All right, hello and welcome. Today, we're going to put on our detective hats. Why? Well, because the world around us is just packed with little mysteries. And guess what? Physics gives us the exact tools we need to solve them. We're not just going to be memorizing formulas today, we're going to learn how to see how things actually work. So, let's get started.
Our very first case is a feeling I guarantee you've had. You step into an elevator, the doors slide shut, and as it lurches upwards, you suddenly feel heavier, kind of pressed into the floor. And then, as it slows down to stop at your floor, for just a second, you feel lighter. So what is going on there? That's the riddle we are cracking wide open today.
Now, every good detective needs a toolkit. And for this case, our tools are some of the most fundamental principles in all of physics, the laws that explain why things move the way they do. So let's go ahead and open up that toolbox.
First tool up, the idea of net force. Just imagine two people pushing on a box from opposite sides. If they both push with the exact same strength, the box isn't going anywhere, right? The forces cancel each other out, and the net force is zero. But if one person pushes just a little bit harder, the forces are now unbalanced. There's a net force, and the box starts to move, or in physics terms, it accelerates. It's that total unbalanced force that's the real game changer.
And this brings us to the master key in our whole toolkit, Newton's second law. It's all summed up in this one beautiful little equation. It basically says that the net force acting on an object is equal to its mass times its acceleration. This is the direct link, the secret connection between force and motion. If you know any two of these, you can always figure out the third. This equation is going to be at the heart of our entire investigation.
Okay, so an equation is great, but to actually use it, we need to know which forces we're even talking about. And that's where our next tool comes in, the free body diagram. It sounds kind of technical, but really it's just a super simple sketch. We draw our object, and then we draw arrows for all the forces acting on it. It's like a visual map that helps us organize everything so we don't miss any important clues. All right, our toolkit is assembled. We've got net force, we've got Newton's second law, and we have our diagramming method. With these powerful tools in hand, let's head back to that elevator and finally solve this riddle. So here's our scene. We've got a person who is 75 kilograms and they're standing on a scale inside an elevator. Let's use our method and draw out the forces. First, you've got the force of gravity pulling the person down. We call that their weight. But then, pushing back, you have the floor of the scale pushing up. And here is the absolute key clue. A scale doesn't actually measure your weight. It measures how hard it has to push up on you to hold you in place. We call that upward push the normal force.
Okay, time for a quick pop quiz. Let's say the elevator starts accelerating upward. Is that number on the scale going to go up, go down, or stay exactly the same? Think back to that feeling of being pressed into the floor. What do you think? Go ahead and lock in your answer.
And the answer is, the scale reads more. If you guessed it goes up, you are absolutely right. You feel heavier because for that moment, the scale is literally pushing on you with more force. Now let's use our toolkit to prove exactly why that happens.
Let's crack this case, step by step. We always start with our master key, F net equals ma. Now looking at our little diagram, the net force is the upward push from the scale, which we'll call Fs, minus the downward pull of weight. Now think about it. For you to accelerate upward, that upward push has to be stronger than the downward pull. So the scale doesn't just have to support your weight, it has to give you an extra push to get you moving up. That extra push is the ma part. And when we plug in the numbers, we see that extra force makes the scale jump up to 825 newtons.
So the huge takeaway here is that your apparent weight, what the scale says, only changes when you are accelerating. When the elevator is just sitting still, or even when it's moving at a constant speed, the acceleration is zero. The forces are balanced, and the scale reads your normal weight. But the second it accelerates up, the scale pushes harder. And when it slows down at the top, which is actually a downward acceleration, the scale pushes less, and you get that fleeting feeling of being lighter.
And this just perfectly shows the difference between mass and what we call apparent weight. Your mass, the amount of stuff you're actually made of, that never changes. But your apparent weight, that feeling of being heavy or light, is really just the normal force pushing back on you. And that force changes anytime you accelerate. Case closed.
So, we've totally mastered forces in one dimension, just up and down. But what happens when forces start pulling at an angle? To expand our detective skills, let's take on a brand new case, the mystery of the suspended traffic light.
Okay, here's the new crime scene. We have a traffic light just hanging there,
motionless. Now that's a huge clue for a physics detective. Motionless means zero acceleration, which means the total net force on it has to be zero. We call this special state equilibrium. It's being held up by two different wires at two different angles, and our job is to figure out the tension or the pulling force in each of those wires. And since the angles aren't the same, it's a safe bet the tensions won't be the same either.
So how in the world do we deal with these diagonal forces? Well, we use this absolutely brilliant strategy. We break each of those angled forces into two simpler parts, or what we call components. We figure out how much of the force is pulling sideways, that's the horizontal or X component, and how much is pulling up and down, the vertical or Y component. It's like turning one complicated problem into two much simpler ones.
Now, because our traffic light is in equilibrium, it means everything has to cancel out perfectly. All the horizontal forces have to balance out. Any pull to the left has to be canceled by an equal pull to the right. It's a stalemate. And all the vertical forces have to balance. The total upward pull from both wires combined has to perfectly equal the downward pull of the light's own weight.
So after we set up and solve our two balance equations from the X and Y directions, what do we find? Well, we find that the first wire is pulling with 108 newtons of force, and the second one is pulling with 132 newtons. Notice how they're sharing the load here. Neither one has to support the full 147 newton weight of the light all by itself.
But hold on, why is the tension in the second wire greater? It all comes down to the angles. The second wire, at 45 degrees, is steeper. It's more vertical, so it's doing more of the vertical lifting needed to fight against gravity. The first wire is at a shallower 30-degree angle, so a lot more of its effort is just being spent pulling sideways. The math confirms what our gut tells us. The steeper wire does more of the heavy lifting.
You know, we've just solved two very different mysteries, one involving acceleration and one in perfect equilibrium. But if you think about it, we use the exact same logical approach for both of them. Let's formalize that approach into a 5-step strategy that you can use for pretty much any problem involving forces.
Here it is. This is the 5-step method that will work every single time. Step 1, figure out what your object is. Step 2, draw that free body diagram of all the forces. Step 3, set up your X and Y axes. Step 4, apply F net equals ma for each axis separately. And finally, step 5, solve the equations for whatever you're looking for. This methodical approach is your key to cracking any physics case.
And you know what the best part is? This isn't just for elevators and traffic lights. This exact same method applies to almost everything you can think of. You can use this to analyze the forces on a tugboat, the acceleration of a soccer ball, or even the incredible thrust needed to launch a rocket into space. It is an unbelievably powerful way of seeing the world.
The ultimate takeaway from all of this is actually pretty simple. If you can understand the forces acting on something, you can predict its motion. The world is just filled with these physics riddles, everywhere you look. Now that you have the detective's toolkit,